let's look now at our continuation of compounds and their bonds. We've looked and talked about ionic. Now let's look and talk about covalent. I introduced these in the last chapter, or the last section, so let's continue on here. So covalent bonding. As a reminder, the difference between ionic and covalent. Ionic is a complete transfer of electrons, for instance, between a sodium atom. Once it loses an electron, it becomes a cation, and it transfers that electron to a chlorine atom, which, once it gains the electron, is a chloride ion, and they formed an ionic bond, a very strong attraction between the positive cation and the negative anion. And that's our ionic, a complete transfer of one or more electrons. But in this section, we're going to look at and talk about the other type of bonding, the covalent, where atoms are being shared. And I showed this in the last section, and these, just as a reminder here, these are non-metal to non-metal sharing. The metals transfer electrons. The non-metals share between each other. So that's what we're going to be looking at. And so, for instance, here's fluorine as an atom. Remember the dots around the symbols? Those are the valence electrons. They're outermost electrons. Fluorine has 7. Each fluorine has 7, and the goal, remember, is octet of 8. Well, each fluorine really wants to find 1, and if you only have let's say a container of fluorine, no metals present to actually give 1 away like sodium might, well, the 2 fluorines say, hey, better than nothing, we'll come together, we'll share, and when we share, for instance, if you're looking at the Lewis structure here, share a pair of electrons, essentially, they're both happy. They're satisfied with an octet of 8, or 8 electrons around them. But that sharing of electrons makes, as we know, what we know as a bond. Okay, we call that a bonding pair. So if we're looking at these things called Lewis dot structures, as a reminder, let me erase all this, clean it up. So Lewis structures have the symbol of the element, like fluorine, and has dots. That's why it's called electron dot. And then you have actually a couple of options. In terms of showing a bond, you can show the 2 dots, like right here, between the fluorines. And because the 2 dots are positioned between the 2 symbols, we assume that's a shared pair. Or you can draw a bond as a line, okay? So either or, in terms of drawing a Lewis electron dot structure for bonds, you can either show the dots between the 2 symbols, that's assumed to be a bonding pair if they're between the 2, or you can draw a line or multiple lines, as we're going to learn that is also sometimes the case. Now, what about all these extra dots around fluorine? So each one of these fluorines came to the table with a total of 7 electrons. Only these single guys end up being shared to make a single bond. The other 6 in total electrons around each fluorine are still there. They're not being shared with anyone. We call that a lone pair. So in this, if we're looking at the whole thing here, fluorine, each fluorine atom in the molecule, each fluorine has 3 pairs, or 3 times 2, total of 6 non-bonded electrons. But we typically deal with electrons in pairs, whether it's a bonding pair, meaning they're being shared between atoms, or a lone pair. You're always going to see them in 2s. Okay? Now, fluorine, two fluorine atoms come together and make a fluorine molecule. And so, again, either one of these would be our Lewis dot or Lewis electron dot structure. Either one would be correct for an F2 molecule, but the chemical formula would be F2. So this is my chemical formula. But this, either one of these 2 that's in the red box, those would be the dot structures. Either one would be correct. I talked about diatomics before, but just as a reminder, and you may go, you did talk about diatomics. When did you talk about diatomics? I I talked about them in our ionic section, but let me refresh your memory. I gave this funky word, Brinkelhoff, and the word Brinkelhoff has the symbols for the 7 elements that are diatomic in nature. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. These 7 elements, when found in nature, are diatomic. So for instance, the air that we're breathing right now is made up about 78% by nitrogen, which is N2, and about 21% oxygen, which we would represent as O2. So in other words, there aren't just single oxygen atoms floating around in the air that we're breathing right now. Oxygen, nitrogen, and any of these 7 are most stable when they're in a pair, and in a pair with themselves. So those are the 7. Some stats about here, some information right here. These are all either gases, liquids, or low melting solids compared to ionic compounds such as sodium chloride or other salts like magnesium chloride, things like that. The interactions between separate molecules is generally quite weak. Okay. Carbon compounds or organic compounds are compounds containing carbon combined with other elements, and almost always these other elements are non-metals. We're going to look at lots and lots of carbon compounds in later chapters, or maybe sometimes if you take another class even. For now, we're going to stick to the basics. Okay, so carbon. Carbon is in column 4 on the periodic table. So carbon has 4 valence electrons, as it can state right there. And carbon almost always forms 4 bonds, either to other carbon atoms or to other elements. This example right here, methane, carbon is sharing with a hydrogen, a hydrogen, a hydrogen, and a hydrogen. Now, if we think about hydrogen, I didn't talk about it, hydrogen's in column 1. Hydrogen has 1 valence electron. Each carbon has 4. So if we were to look at the dot structure for carbon just alone, it would look like that. Remember, it wants to have 8 total around it, satisfying the octet. Well, if you put 4 hydrogens around it, and remember each hydrogen also comes to the table with a single dot because of the 1 valence electron, that's what forms the CH4 molecule, commonly known as methane. And that's what carbon typically does. Nitrogen actually has 5 valence electrons. Remember, it's in the column 5A. So to complete its octet, it needs to find 3 more. 5 plus 3 is 8. It does this by sharing 3 of its own. So for instance, in NH3, you've got nitrogen going to 3 hydrogens. Again, each nitrogen comes to the table with 5. Okay, you can depict them in several ways. There's one way. You can put the dots, remember, around any side you want. And each of the 3 hydrogens has 1. So 1 hydrogen will come here and make a pair. A second hydrogen will come here and make a pair. A pair of electrons, remember, is a bond between the 2 atoms. And a third hydrogen with its 1 valence electron will come here and make a pair. I don't need a 4th hydrogen because the pair that was already there around nitrogen. And you never want to have, if you can avoid it, you never want to have more than 8 around any given element. And we'll talk more about the exceptions to that later. But with each hydrogen donating 1, 5 from nitrogen plus the 3 from the 3 hydrogens total, 5 plus 3 is 8. And so again, when we look at Lewis structures, these would be the 2 correct or accepted Lewis structures for NH3. Again, depending if you want to show dots between everything, or if you want to show lines, any place you have a bond, you can do either or here. Okay. Now notice I still have a pair, a lone pair on nitrogen. Whoops, oh, you guys, sorry, this should be a hydrogen. I still have a lone pair on nitrogen because this pair over here that was unshared, well, that still remains. I only had N1H3, so 3 hydrogens, the 1 nitrogen. Here are some typical bonding patterns. Just doesn't say strict rules, but typically For instance, carbon has 4 bonds. Now, those 4 bonds, I should warn you, can be single, double, triple. We're going to talk about multiple bonds later, but it's still, the quantity is, what does it usually look like? Nitrogen typically has the 3 we just looked at, and therefore the lone pair. Oxygen, let me erase all this. Oxygen typically has 2 bonds, and actually quite often the Lewis structure where oxygen is the central atom, it typically looks like that. Fluorine and any of the halogens, they typically look like this, a single bond. And then they have 7 valence electrons, so 1 electron is here in the bond being shared. Remember that F2 example I gave a few slides back? And then has the 3 lone pairs. So again, these numbers that I'm circling right here, these were from the tops of the columns on the periodic table for these elements underneath it. So all the halogens have 7 valence electrons. Oxygen, sulfur have 6. Nitrogen, phosphorus 5. Carbon, silicon 4. And boron 3. These are non-metals we're looking at. And so you can see then, if we go to these examples over here in this table, you can see, again, this is typical. Carbon with 4 bonds, nitrogen with the 3, and oxygen with the 2. And so again, octet needs to be satisfied. Oxygen has a total of 6 valence electrons. So if we're looking at oxygen by itself, oxygen, however you want to throw 2, 3, 4, 5, let me give another one a pair. So oxygen, just oxygen alone would look like this, an oxygen atom with 6 valence electrons, 6A. And so oxygen is looking for 2 more. I just made them in blue. Where can they get 2 more? Typically from an atom with just 1 valence electron, like hydrogen. So H2O, everyone knows what that is, water. That's where it comes into play. 2 hydrogens helping out oxygen to get a total of 8 around it. Even if it has to share them, that's okay. It's still, the goal is 8 for octet. And then one other thing, you guys, I wanted to show you. Down here, what I'm just kind of, let me see if I can blow it up a little bit without turning this too crazy. So these are molecular models. We're not going to play with molecular model kits in this class. However, if you've got a kit and, if you happen to have a kit or you want to buy one, you can make models. Models are basically, they look like little kids' kind of tinker toys, but they're plastic balls that represent atoms. Sometimes they have plastic sticks as well that would represent bonds, but molecular models allow you to visualize what the 3D structure of any given molecule is. So it's quite useful. All right, so we're trying to look at these things called Lewis dot structures and determine how, when elements or atoms come together, how do they make the molecules that they do, like H2O or NH3. Okay, so if I'm looking at, let's say the question is, draw the Lewis structure for CO2. So a couple things you need to do. You need to look up how many valence electrons each atom has in the particular chemical formula. Each carbon's in column 4A, each carbon has 4 valence electrons, so carbon's total is 4. Oxygen is in column 6A, but in this chemical formula there's 2 oxygens, so that's 6 times 2 is 12. So in total, CO2 needs to have 16 valence electrons. Okay, so when we're doing these, called again Lewis dot structure, I'm going to run out of room, so we're just going to call it Lewis dot. A couple of things you have to be mindful of, and that is total valence electrons. That's what I did right here. This was my total for CO2. And you need to be mindful of octet, that for the most part everything wants to have 8 around it. Whether they're being shared or whether they're those lone pairs, doesn't matter, but the goal is 8 electrons. Okay, now, before we even get to that, first thing you've got to figure out is how do you arrange them? 1 carbon and 2 oxygen, what goes in the middle, how does it work? Well, typically, you look for whether there's one element that there's only quantity 1 of. So let me say that again. You take the chemical formula, you look at the formula, decide, is there one element with a quantity of only 1? And if so, that's the guy who goes in the middle. I kind of like to say he's the only child, and only children always love to be the center of attention at parties. So your only child goes in the middle. And next to it, again, depending if you want to do lines or dots, on each side of it, attach an oxygen. Because I have 2 of them. The chemical formula told me I had 2. I've got to attach 2 of them. Now, we're going to look at some other examples in a little bit, but this works for our CO2. Okay, so you connect them. Then, now we start playing with the electrons. So, as I said, these are my big rules here. I've got to obey octet. I can, for the most part, usually not have more than 8. And I need to satisfy the total valence count. In this instance, it's 16. So, before I do anything else, let me look at what I've done so far. I have carbon with a bond to each oxygen. Remember, every single line bond is 2 electrons. Okay? So, if I stopped right here, this would be CO2 with only a total of 4 electrons being depicted. I need, remember, 16. So I'm nowhere near where I need to be at. So my total valence electron count is not accurate at this point. And the octet, well, nobody has 8 electrons around them. This oxygen here only has 2 that it's sharing. Carbon in the middle has 2 plus 2 or 4, so that's not the octet. And the oxygen on the right-hand side also only has 2 that are being shared. So nobody has an octet either. That tells me that I'm not just ready to go with connecting the atoms. Okay, let me clean this up a little bit and go back to my drawing. Okay, so I have carbon going to an oxygen, going to an oxygen. Okay, so this is where you start adding the dots. Okay, you start adding the dots. And so right now I'm showing 4 electrons. 16 minus 4, I've got 12 dots left to place. And you can kind of play with it at first. I always recommend you use a pencil when you do this. Okay, so I need to put 12. I don't care, wherever you want to put them. 2, 4, there's 6, 7, 8, 9, 10, 11, 12. Okay, so I start out, everything's connected, and right now I have 2, 4, 6, 8, 10, 12, 14, 16. My total valence electron count is good. I'm at 16. But remember the rules that I have over here. Both total valence electron count has to be accurate and octet. And if both of those are correct, then you know you've got a good, correct, accurate Lewis structure. So let's check octet. All right, we'll start with carbon in the middle. Carbon has 2, 4, 6, 8. A total of 8 electrons around it. Carbon has an octet. We're good with carbon. Check the box. But oxygen, and since they both look the same, I'm just going to pick one of them. Oxygen has 2, 4, and the bond is 6. Oxygen on the left or oxygen on the right, they only have 6 electrons around them. So I have not satisfied the octet rule, which means this is not a correct Lewis structure. And here's where you'd get your eraser out and start editing a little bit here. Let me erase some of this. You know what, I'm going to start again. All right, so I know it's got to be carbon to the 2 oxygens, okay? But with a single bond between them, that didn't work. You always start with single bonds and dots. And if you can't obey both rules, both of these were not correct, you go back to the drawing board. If single bonds won't work, then you try double. And you try one at a time, okay? One at a time. So even though you can see right here, that's actually what the final thing is going to kind of look like. I'm going to try it one at a time because you don't always do it symmetrically, meaning everybody gets a double. Okay, so add one at a time. So, okay, I've added one bond. And so now 2, 4, 6 electrons are being shown in my single lines, in my bonds. But I have to do 16. So I have 10 more left to place. 2, 4, 6, 8, 10. All right. Boom, I'm out of electrons. And you can count 2, 4, 6, 8, 10, 12, 14, 16. My 16 is good. Again, this drawing has a check the box, total valence electrons, correct. Okay, but octet, remember, I also have to check the box for octet before I can move on and say this is a good Lewis structure. Well, 2, 4, 6, this oxygen right here, as it's drawn, does not obey the octet rule. Whoops, no octet. So I can stop right there. This cannot be a correct Lewis structure. Now, just to practice, we'll check the other two. 2, 4, 6, 8. Carbon is good for octet. 2, 4, 6, 8. This oxygen's good for octet. So I'm getting closer, but I'm still not quite there. Back to the drawing board. Let's erase all this. All right, so carbon, whoops, the 2 oxygens. I was getting closer when I added my multiple bonds, so let's do 2 double bonds, and let's just make it symmetric. You could try a triple. That's the most you can have, but you could try a single and a triple. But I like to make things even and symmetric, so let's make both sides a double. And before I start adding my dots, remember, 16 is my total. I've got 2, 4, 6, 8 in bonds right now. 16 minus 8 is 8 more to place. Now be careful, be careful. Carbon, right now with just the bonds, carbon has 8 around it. Carbon has an octet. I can't give carbon any more dots for those lone pairs. But each oxygen only has 4 electrons around it. So each oxygen has room for 4 more electrons, and you can put them wherever you want to put them. But remember, you always put them in pairs. So here's what I've got. Okay, that's where I'm at right now. Now let's check our work. Total valence needs to be 16. 2, 4, 6, 8, 10, 12, 14, 16. Again, check the box. Valence total is good. Now let's check octet. 2, 4, 6, 8. This oxygen is good. 2, 4, 6, 8. Carbon is good. 2, 4, 6, 8. Oxygen is good. Octet is also correct, so even though I've got scribble all over it, that's the correct Lewis structure for carbon dioxide, CO2. Question down here, what about sulfur directly below oxygen? What if I had an SO2 molecule? Would it look the same? Well, it sure would, and that's because sulfur, if I change this to a S for sulfur, sulfur is also in 6A. It would have 6 valence. Whoop, oh, yeah, oh, wait. Sorry. It would be CS2. Sorry. I still have the 1 carbon, 4 electrons. Sulfur is in 6A like oxygen, so that becomes 6 times 2 is 12. My total would still be 16, so my total valence is still 16. It's octet, has carbon in the middle, all that good stuff. So sure, it would look exactly like it. It would be SCS with the 2 lone pairs on each. Okay? So in other words, again, where the elements are on the periodic table is really important. Helps you to just determine total valence, and then there's some similarities in things too when you start changing elements out, like change or swap an O for an S. All right? So this is what it looks like. And I explained it on the last one, but it looks exactly the same. Sulfur was in the same column as oxygen, very similar properties, same number of valence electrons. All right, how about N2? Okay, so I know you can see everything down below, but let's start at the top. If you're given the chemical formula N2 and you need to draw a Lewis structure, first thing we need to get our total valence. So there's nitrogen. Nitrogen's in column 5A, and there's quantity 2 in the chemical formula N2. And in fact, that's all there actually is in this particular molecule. So my total valence electrons needs to be 10. Okay, get your total valence and then connect the atoms. Well, this one's pretty simple. There's only 2 nitrogens, so that's how they connect. And you always, again, did I say always? Always start with single bonds and dots. Okay, and try that first. So my single bond is 2 electrons. 10 minus 2, I have 8 left to place. 2, 4, 6, 8. There's lots of options how you want to put the 8, but you put 8, and then you go, okay, remember let me put it down here, you've got to obey octet, and you've got to watch your total valence. Okay, so I put a total of 10, so that's good. But octet, now here's where we're going to get caught up. 2, 4, 6, 8. This nitrogen is good for octet. But the other nitrogen, 2 and 2 for the bond, this nitrogen only has 4 electrons around it. If the octet is not obeyed, octet rule, for all the atoms in the molecule, octet does not happen for even one, then I know I have an incorrect drawing, and I've got to go back to the drawing board. So let's go back to the drawing board. Erase all that. Okay, back to my drawing board, so I still know I have N2. A single bond and dots didn't work. So what's the next option? From a single, increase it to a double, and then add dots. So if I have a double, I still need to have 10 valence electrons. A double bond, each bond has how many electrons? 2. So 2 times 2 bonds is 4. So with this, I have 6 dots left to place. And again, put them wherever you want to put them. 2, 4, 5, 6. Okay, now we're going to check our 2 requirements. We have to check octet, and we have to check total, valence. Well, I know my total valence is good. 2, 4, 6, 8, 10. That's, check the box, that one's good. Octet, 2, 4, 5, 6. This nitrogen on the right, again, just because I drew it this way, this nitrogen on the right has 8 that it wants. Again, whether they're lone pairs or sharing, doesn't matter. It adds up and counts. So octet is good for the nitrogen on the right, but nitrogen on the left, 2, 4, 6. Oh, it's so close to 8, but it isn't 8. Octet is not good on the other nitrogen, so octet is not satisfied. I know this is not a correct Lewis structure. Back to the drawing board. Okay. All right. And so last but not least, if my single bond didn't work and my double bond didn't work, last thing you can try is a triple bond. So triple bond, 3 bonds times 2 electrons each, that's 6 electrons. So now I only have 4 dots to place. And let's be nice and generous, everybody gets 2 for a couple of reasons. 1, I only had 4 total to place, but had I tried to put an additional, let's say, pair on nitrogen up here, I would have blown the octet. I would have gone beyond 8. 2, 4, 6, 8. Would have had 10 around it. So that's how I also knew that I couldn't place the other 2 here. Okay. So everybody gets 2. My total is 10. 2, 4, 6, 8, 10. That's good. Total valence 10. And now let's look at octet. 2, 4, 6, 8. This nitrogen has 8. 2, 4, 6, 8. This nitrogen has 8 electrons around it. Again, whether they're lone pairs or sharing, it still counts for octet. So all the atoms in the molecule have an octet, and the total adds up to be what it's supposed to. This is my correct Lewis structure for a nitrogen molecule. All right. So that's drawing Lewis dot structures. Now let's go on and talk about how to write the names. Now, this is actually a lot easier than naming our ionic compounds in the last section. So here's the deal. Just like in ionic, you name, step 1, name the first element as it is on the periodic table. You never change the name. Just like, for instance, let me write this here as our example. For ionic, whoops. So our first element is Na, which the periodic table tells us, or maybe you already know, is sodium. You don't change the name. Step 2, you take the second element, for instance, chlorine, and you change it to chloride, giving it an IDE ending. The same thing works with our covalent. You name the first element, N is nitrogen. You name the second element, but you give it an IDE ending. So oxygen changes to oxide, just like it would if, let's say, I had the ionic compound. Oops, it would be this. NaO2. Sodium is the first element. Oxygen is the second. Oxygen changes to oxide. Whether it's covalent or ionic, the beginning steps are the same. Name the first element as it is on the periodic table. Name the second element and give it an IDE ending. Now, here's where the rules... here's where there's an additional step. if it's covalent, and that is you use these prefixes. So keep these handy. You can have access to them, obviously. Your regular tests, they're open book, quizzes, things like that. So you've got your prefixes. In covalent, and only in covalent, we use these prefixes to indicate quantity. So for instance, anything that has NO in it, if we just named it like we did in ionic, it would be nitrogen oxide. However, there's several different ways nitrogen and oxygen can come together to make molecules. And we've got to be able to distinguish in their names whether it's NO, NO2, N2O4. And so hopefully you can see when you have the quantity 2, you use di. When you have quantity 4, you use tetra, which actually changes, the A drops off, it's tetroxide when you combine it with oxygen or oxide. So you use the prefixes. The very last step in naming a covalent is that you use the prefixes to indicate quantity. And you stick them in front of nitrogen if there's more than one. And let's stop and talk about the 1 for a second. Quantity 1 is assumed most of the time. You'll see sometimes like nitrogen oxide, also sometimes listed as nitrogen monoxide, and sometimes just nitrogen oxide. So the mono, sometimes it's used, sometimes it's not. Okay, just be careful on that. It's really up to the author of the book, or I won't deduct if you use it or you don't. No prefix, assume 1. Okay, but anything other than 1 always has to be used. Okay, it's kind of like when you write a chemical formula. We don't write N1O1. If N is there, we assume there's 1. If there's more than 1, like O2, it would be written. Okay, so here's SO3. Let's practice here. S is sulfur. Name the first piece. Take the second piece, O, oxygen, changes to oxide. And then finally, the last step of a covalent is use prefixes. So S is just quantity 1. So I wouldn't use the 1 typically, or mono, but 3 is tri. So I would stick, and I didn't space it very well, sorry, but I'd stick the tri in front of oxide. So its full name would be sulfur trioxide. I think you'll agree it's a lot easier than the ionic compounds. Here's a table with several more examples, and again you'll see that mono tends to be omitted when quantity is 1. And then just some interesting tidbits of information there, commercial uses of these different substances. Okay, here's some practice for you. I want you to hit the pause button, work these out, and then come back and check your answers and hit play. Okay, so, whoops, oh, I'm sorry, I lost some of my options here. We're going to name these. Forget these options here. Si is silicon. Cl is chlorine, which changes to chloride, but there are 4 of them. So silicon tetrachloride. Mono, again, is assumed. P2O5. P is phosphorus. Oxygen changes to oxide. And then our prefixes. I have 2 phosphorus, so diphosphorus. I have 5 oxygen, so pentoxide. And you'll notice when there's a penta or a tetra next to an O for oxygen, we don't usually put an A next to an O, and in fact the A will drop off. So it's pentoxide or tetroxide, things like that. And then finally, Cl2O7. Well, Cl, now it's written first, so we leave it as chlorine. Oxygen is written second, becomes oxide. 2 chlorines, that's di. 7 is hepta, but again we drop the A because it's next to an O, so heptoxide. Dichlorine heptoxide is the name of the Cl2O7. All right? And then these bottom ones, we're working backwards. Okay? Again, assume you don't know what the answer is. If you're given a name, write the formula. So in A, phosphorus is P. No prefix, we assume quantity is 1. The second one is chloride, which comes from chlorine, and the prefix penta is 5. Letter B, dinitrogen trioxide. Nitrogen and oxygen are the two elements. Dinitrogen means two nitrogens. Trioxide means three oxygens. Finally, sulfur hexafluoride. Sulfur is S. Fluoride comes from fluorine, which is F. There's no prefix on sulfur, so assume quantity is 1. Hexa is 6, and hexa is with the fluoride, so there's 6 fluorides. Okay, now we're going to go kind of the next step here. These covalent bonds, as we've talked about, they're sharing electrons. However, this doesn't mean that they're shared equally. As crazy as that sounds, different elements have different, I like to say, strengths. And if you think about electrons that are being shared, for instance, between hydrogen and chlorine, if you think about that like a game of tug of war, a rope being held between two different elements. Two different elements, like two different people playing tug of war, typically one person is stronger than the other. And one person would be winning the game of tug of war, pulling more of the rope on their side of wherever they were standing and playing the game. And that results in what we call a polar bond. When one atom is stronger than another, they're hogs. They're pulling more of the electrons on their side because they're stronger. There's a difference in strength then between the two, and that leads to a polar bond. And so the bond's made up of electrons. Electrons are negative. So for instance, in my example here with hydrogen and chlorine, hydrogen, we'll talk about why in a minute, but hydrogen is weaker than chlorine. Chlorine is stronger in the game of tug of war. Chlorine is pulling more of the rope on its side. The rope is made up of electrons, so chlorine has more of the electronegativity, more of the electrons on its side, and that leads to what we can depict as, this is the partially, it's the Greek for P, partially negative, because it has, again, more of the electrons on its side, and then that leaves poor hydrogen as partially positive. He's deficient of the electrons, not equal sharing. And we call this a dipole, when there's a difference in strength. Okay, so how do we know who's stronger than who? I just told you hydrogen was weaker than chlorine, but how do we know that? Well, for the most part, it's based on where they're located on the periodic table. The strongest of them all is fluorine. Fluorine is the biggest hog of electrons. Okay? It wants to keep everything to itself. It doesn't want to share as much. This strength, the technical term for it, is electronegativity. And then it's truly based on where the element sits on the periodic table in reference to fluorine. So for instance, phosphorus is weaker than chlorine. Because again, chlorine sits closer to fluorine. Chlorine is stronger. Phosphorus is weaker. Okay. The larger the number as well, the more hoggish the element. Isn't that crazy? So here are numbers in terms of the larger the number. It's these numbers on this particular cutout of the periodic table. So again, fluorine has the largest number of all these. It's the stingiest. It doesn't want to share. It's the strongest. It's going to pull the electrons more to its side. Okay? And then down here, let me pull this up a little bit. If you compare the numbers, for instance, let's say you have a CF bond. Fluorine has an electronegativity of 4.0. Carbon has an electronegativity of 2.5. If you subtract the two, the difference for the CF bond is 1.5. Now, depending on where that number lies, you can determine if you have an ionic bond, like between sodium and chlorine. I'll show you that in a second. In this instance, I had 1.5 difference. That's a polar, unequal sharing. That's a polar covalent bond between carbon and fluorine. If the difference is close to 0, okay, technically if it's really anything less than 0.4, we actually say it's nonpolar, that they're essentially equal in strength. Now an example of that would be if I had, let's say, 2 carbons. Well, each carbon is 2.5. 2.5 minus 2.5, there's 0 difference in strength. 0 is non-polar. Nobody wins the game of tug of war. It's equal sharing between the two. So anytime you have two of the same element in a bond, that's going to be the case, because you're going to have the same electronegativity number. 3 minus 3 is 0. 2.5 minus 2.5 is 0. 3.0 minus 3.0 is 0. Even F2, 2 fluorines, 4.0 minus 4.0, that's 0. Anytime you have two of the same, you're going to have nonpolar. And then there's one other exception, and that is carbon versus hydrogen. Carbon versus hydrogen, you have 2.5 for carbon minus 2.1 for hydrogen. And so while there is a little bit different, a little small difference in electronegativity, this is where our threshold is, okay? And 0.4 and below, it's still a covalent bond. Electrons are being shared, but really if it's less than 0.4, it's considered nonpolar. So we say carbon-hydrogen or hydrocarbon bonds are essentially nonpolar. Yes, there's two different elements playing tug-of-war, but they're essentially the same strength, or close enough that it would be a pretty boring game of tug-of-war, and the electrons would be equally shared. One last one to look at, I talked about ionic and the numbers. Ionic, sodium chloride, for instance, my favorite ionic compound. Sodium is a 0.9, chlorine is 3.0. So 3.0 minus 0.9, the difference in electronegativity on that single bond there between them, or just the two atoms, 2.1. Okay, definitely falls in the ionic range, which we should have known anyways because it was a metal to a nonmetal. Sodium is my metal, chloride is my nonmetal. Okay, so now we're going to talk about going a step beyond what we just looked at, and that is taking these individual bonds and whether they're polar or nonpolar and looking at molecules. Now remember, when you have two of the same thing, the electrons are shared equally. It would be like two twins playing tug-of-war. Nobody would win the game of tug-of-war because two of the same thing pulling equal and opposite. So the H2, the Cl2, two of the same thing, equal sharing. The hydrocarbon I talked about on the last slide, although you have two different elements, carbon and hydrogen, their strengths are so similar that it results in essentially equal sharing, not enough to make a difference and to make a polar bond. And then you can see these other examples right here where we have unequal sharing. It's a covalent bond because it's a nonmetal to a nonmetal, but one element is stronger than the other. And the guy who is stronger, for instance, bromine, gets the partially negative symbol, and the guy who is weaker, hydrogen, gets the partially positive. And again, that's because if you think about the bonds, and if you use the analogy of the game of tug-of-war, bromine is stronger. He's winning the game of tug-of-war. He's pulling more of the rope to his side, and the rope is made up of negative electrons. So if he has more of the rope, that means he has more of the electrons, and electrons are negative. He hasn't completely taken the bond or all the electrons away. It's just an unequal sharing, and it favors the stronger, the more electronegative element. And then these guys down here, metals to nonmetals, those are ionic, as it says over here, because I've got a metal completely giving away an electron. All right, so let's look down here at this question. Predict if the following are polar or nonpolar. Well, just a fluorine to fluorine, two of the same thing. Can you look up here and determine where that would fit? That's right, it would be nonpolar. But what about my CO2? Well, CO2, what happens, and if I were to actually draw the full Lewis structure, we actually have two polar bonds, okay, with the dipole or the arrow pointed in the direction of the stronger element. Or another way to represent this, again, is with the partially negative, partially positive signs. But what happens, I have equal and opposite pull. And so think back to your math days, and the vectors will actually cancel when you have equal and opposite. So this CO2 is an example of a molecule with polar bonds. This is polar and this is polar. But when you look at the whole molecule, it cancels and you have a non-polar molecule. So in fact, both the fluorine and the carbon dioxide are non-polar. Okay, So now that leads us into looking at the shapes of the molecules. These Lewis structures that we've been looking at so far, these electron dot structures or Lewis electron dot structures, depict the arrangement of the electrons and whether they are bonded or shared or whether they're non-bonded or what we call lone pairs. But it gives it on a two-dimensional flat surface. And in reality, molecules are three-dimensional. So once you have this electron dot structure, you can take it a step further and predict the shape of the molecule. But you've got to have that Lewis dot structure first. All right, so a couple things about the shapes, as you can see here. All diatomic molecules are linear since the 2 points determine a straight line. Or anytime you have just two atoms, okay, A going to B, whether they're both the same, such as AA, like in the diatomic case, or whether they're two different elements like AB, if you just have two, okay, the bonds are straight, they're always linear, straight line. However, what if we look at two atoms bonded to a central atom? Now, what you're going to learn here, and what I should have really started with here, is it doesn't matter what the actual atoms are in determining shape. You're going to be looking at quantities and bonds versus lone pairs. So that's why, for instance, right here, I use the letters A, B, and C. And A, other than B boron, A and C are not actual elements. And it doesn't matter. We're going to be looking at a central atom and how many things are attached to it. Okay, so right here we're talking about two atoms bonded to a central atom. That's this guy right here. My central atom, the guy in the middle, is the letter B. Or, for instance, if I was talking about carbon dioxide, carbon is the central atom. Suppose that the two atoms not bonded together repel each other. What relative geometry would minimize the repulsion, a bent or a straight line? Well, so in other words, here's what's going on. Two oxygens, both considered to be partially negative, they're going to repel each other. They want to be as far away from each other as possible, as do the electrons in these bonds. Electrons are negative. They're going to repel each other. They want to get as far away from each other as possible. And all of these shapes we're going to look at, the atoms and the bonds are maximizing the amount of space or distance between them. So when you just have a central atom and two things attached to it, the maximum space is to keep them 180 degrees apart. And when they're 180 degrees apart, that makes a linear shape. Or you could again draw a straight line through it. That's where linear comes from. Okay, what if the central atom has three things attached to it and they repel each other? What would the geometry be? Well, here's my central atom. Again, it doesn't matter what it is. Three of the same thing, bonded to it. Again, maximizing the space. Well, I've got not two. If I had a central atom with two things attached to it, it had a 180 degree difference. Well, now I throw a third thing in there, and it's only going to have 120 degrees of separation. I think about, for instance, kids in a house. And if you're an only child, you get the whole house, well, you and your parents, you get the whole house to yourself. However, if you get a sibling, now you've got two kids that have to share the space. Throw three kids in there, and every time you add more kids to that same house, there's going to be less and less individual space that you get in the house. So the same thing idea applies here. As we add more things, as we add more atoms directly attached to the central atom, you're going to notice they get closer and closer. Now, in terms of the shape, if you actually have a model kit, you can create this, and if you put this together, this is actually a flat molecule. That's where the word planar comes from. The word trigonal comes from the fact that if you were to connect the three outers, you notice what shape that makes? Makes a triangle. So trigonal planar. Now, if they are the three of the same, okay, if they are three of the same thing because it's flat, again, the vector idea, if you have three polar bonds, like let's say you had BF3, okay, fluorine is stronger than the boron, you would have a polar bond in each of the three where fluorine is pulling away from boron. The three vectors, because it's flat, would actually cancel. And so this results in let me erase all my scribble here. It results in a non-polar molecule. Again, they have to be 3 of the same things attached to the central atom. Non-polar. Now, what if I had this guy here? Again, I don't actually even tell you what the atoms are, but I have some central atom, whatever it is in pink. I have 2 of the same thing. Maybe those are hydrogens. And then I have a guy up here who's different. Different color indicates a different atom. Well, now I'm not going to have equal and opposite. It's basically asymmetric. So this will result in a polar molecule. So that's what I was just talking about right here. What if only 2 of the 3 are identical and the third one is different? That's when you get a polar molecule. And then finally, when we add a 4th identical atom to a central atom, so for instance, CH4 would be carbon in the middle of 4 hydrogen. My Lewis structure would look like this, what I just drew. However, when I actually put it together, I get a tetrahedron shape, geometric shape. Okay, and again, going from a house with 3 kids to a house with 4, you're going to see there's less space between them. In fact, it's 109.5. The bond angles get smaller and smaller because you've got more atoms around the central atom. There's going to be less space for them to get away from each other. So here is an example in ammonia, NH3, you've got 3 hydrogens and a lone pair of electrons. The question is, do the lone pair of electrons behave as an atom as far as geometry? Well, a lone pair of electrons appears to act as an atom as far as geometry. Well, that's because lone pair electrons take up space. So for example, even though I don't have it shown here, this is the shape, and this big space up here is where the lone pair electrons reside. They're electronegative. They're going to be repelling the electrons in the bonds between nitrogen and hydrogen, so they're pushing them down. So they definitely contribute and affect the shape of the molecule. Okay, what about water, which has 2 lone pairs and 2 atoms for a total of 4 groups? So in other words, this is our page where we're looking at central atom with 4 groups, or I sometimes just call them 4 things attached. Well, what happens with water? Well, Lewis structure, you can draw it like this, and this is a correct Lewis structure. However, it is not actually a linear molecule. Again, if you were to grab a kit and put it together, or think about what happens anytime you have a central atom going to 4 things, whether the 4 things are atoms or whether they're lone pair of electrons, they all factor in and affect the shape of the molecule with respect to the central atom. And so when you have a central atom with 4 things, including the lone pair of electrons, it has a tetrahedral. Again, that name comes from the geometric shape tetrahedron shape. So to determine the geometry around the central atom, you've got to, again, first have the Lewis electron dot structure. Then you count the number of groups that surround the central atom. A group is, or I just call it a thing, it's either an atom or a lone pair. So if you have 2 groups attached to a central atom, you've got a linear geometry. If you have 3 groups or things attached, you've got a triangular, or sometimes called trigonal planar geometry. And if you have 4 groups attached, that's what's called a tetrahedral geometry. And again, it's all with respect to the central atom. And again, just to give you an example, and I'm not even going to tell you actual elements because it doesn't matter. You're looking at a central atom going to 2 things. This is linear. A central atom going to 3 things. This is the trigonal, or sometimes up here what's referred to as triangular planar geometry. And then a central atom, let's pick some new letters here, going to 4 things. This is the tetrahedral geometry. Okay, so in shapes of molecules, to continue on with this, there are a number of other additional geometric patterns that atoms can form bonded to central atom. The structures of the linear carbon dioxide, the pyramidal ammonia, bent water, and tetrahedral CH4 we have just described are the most important for us in this class. So we're going to kind of take this a step further. So water, again, if you look at this here, this is the actual molecular model of it if you were to get a model kit and put it together. And again, it has this bent shape because even though when the model doesn't depict it, you have to imagine and realize there's two lone pair of electrons around the top here. So with respect to the electrons, being the electrons in the bond and the electrons lone pairs, this is tetrahedral with respect to all the electrons. But when we think about it just in terms of the atoms, this is the, whoops, you guys probably can't see that very well. This is a bent shape with respect to the atoms, or we call that molecular geometry. And again, ammonia, we have to realize there's actually some lone pairs here. So again, with respect to or including the lone pairs, the electron domain geometry here is again tetrahedral, central atom going to four things. However, the true molecular geometry, if we just look at what the shape is with respect to the atoms, this guy here, this is that trigonal pyramidal, forms like a little pyramid. And then finally, methane, again, central atom going to four things as well. So tetrahedral. But because all four are atoms, it's tetrahedral with respect to both the electron geometry and the molecular. So be careful of that. Again, one more time, the difference between the electron domain geometry and the molecular geometry. The electron geometry takes into account the lone pairs, like on water, and the fact that you go, okay, central atom goes to four things tetrahedral. But the molecular geometry is, if you were just to draw a line and look at the shape of the molecule with respect to the atoms and the bonds, what's that shape? And again, for water, as I've scribbled all over here, that's bent. For ammonia, tetrahedral with respect to this fact that there's central atom going to four things, but when you look at the molecular shape, just in regards to the atoms, it's trigonopyramidal. And then methane, since the central atom goes to four things and they're all atoms, it's tetrahedral for both electron and molecular. Okay, heats of fusion and heats of vaporization for selective substances. We're going to come back into this, especially when we talk about energies and things like that. But I just wanted to kind of introduce it right now. Heats of fusion and heats of vaporization. So everybody probably knows what vaporization is, right? When you go from a liquid to a gas. That takes energy. It takes energy to overcome. There's intermolecular forces of attraction between molecules, and you have to apply energy to do that. Heat of fusion, you may not realize what this is, but fusion is when you go from a solid to a liquid. So this is fusion, this is vaporization. And again, it takes energy to, say, melt an ice cube, going from a solid to a liquid. And so for the different substances, you can just obviously see their chemical formula, but you can also then see what they melt at, and then their heats of fusion. Again, how much energy is in joules, how much energy it takes per gram of that substance to go from a solid to a liquid form. Or if we're talking about going from a liquid to a solid, let's say freeze an ice cube, it's the opposite. It's going to release this much energy. And then the boiling and heat of vaporization, so this is the temperature at which these substances, under normal standard conditions, will boil. Heat of vaporization is how much energy does it take to go from a liquid to a gas. Or again, vice versa, maybe you have a gas and you're going to condense it back into a liquid. This is how much energy then is released when that process happens. And as you can see here at the bottom, the statement, the properties of water are anomalous in comparison to other similar substances. This is due to a property that is referred to as hydrogen bonding, which we're going to discuss later. So really here as well, this last sentence points out, notice the differences in the melting point between, let's even just say water and, you can't see it from methane, sorry, but water and ammonia, NH3, they're very similar in size. Fairly similar in shape, but yet their melting points, their boiling points, their heats of fusion, relatively similar, but the heat of vaporization is drastically different. The melting points, boiling points are drastically different. And we're going to learn about hydrogen bonding in another chapter. Okay, so these forces that we're going to look at here eventually, tying in with what we're doing now and what we're going to do, here's a summary of the attractive forces between an atom. Okay, ionic forces, so for instance, between a sodium ion and a chloride ion. Covalent chemical bonds, so that would be, for instance, triple bonds as in nitrogen, double bonds in the carbon dioxide, and single bonds in methane. So again, these are chemical bonds, and those are obviously forces of attraction. Ionic is the strongest, okay? So this is strongest or stronger at the top, weaker at the bottom. And then hydrogen bonding, we're going to talk about later. These dipole-dipole interactions, that's what happens between two polar molecules. And then the weakest of all the forces are dispersion forces. And so basically, just to kind of give you an intro here, everything has dispersion. It has to do with the electrons in an atom, and as we know, all atoms have electrons. Dispersion forces just deal with those electrons. So everything has dispersion. Only polar molecules undergo dipole-dipole, and that's, as you can see from this picture that I'm going to clean up here for you. Polar molecules have one side of the molecule that's partially negative, one side that's partially positive. That's the definition of a polar molecule. However, in a sample, even like, let's say, a single drop of HCl, there are millions and billions of molecules of HCl. And so you're going to have lots of these attractions going on where one HCl lines up next to another HCl, and you'll notice how they line up, that this partially negative here lines up next to the partially positive on an adjacent molecule, because even though they're even partially negatives are going to repel each other. Partially positives are going to repel, but a positive and a negative would attract. And then finally, hydrogen bonding we're going to talk about later, but as you can imagine, it involves hydrogen, but it's not just hydrogen. You have to have the extremely polar bond HO, HN, or HF present. And that has to do with the differences in polarity being so great between these two atoms in one of these three, HO, hydrogen oxygen, hydrogen nitrogen, or hydrogen fluorine. Okay, and that concludes this section and kind of gives you an intro into what we'll be looking at in the future.